Uh, I'm going to speak about non-parametric estimation of diffusions in the low frequency setting, which I'm going to explain in a second. And I'm a first year PhD student working with Richard Nickel. Yeah. And so let me first introduce the setting before we go to the mathematics. What is modeled by these diffusions is, for example, a pollen grain moving in water. So imagine there's a pollen grain in a water stream. Then there are two components that contribute to the motion of the pollen grain. The first component will be some random motion that the pollen has. It's jiggling around. And the second component of the movement is going to be, some kind of general drift it has following the stream of water. And how is this mathematically modeled? Oh, wrong button. It's modeled by this stochastic differential equation, which reads dxt, where xt is the path of the pollen, equal to be the sum of these two terms, where b is the drift function that's modeling the water flow profile, plus this Brownian motion term, which is random. So the solution to the stochastic differential equation will be a diffusion process. And now if we look at it from a statistical perspective, we're given this equation in the background, but we don't know the water flow profile or the drift coefficient b. But what we're given is observations of the pollen grain at discrete times. So suppose we've placed a sensor on it, and in time intervals of delta, we collect the positions of this particle. And from these observations, we want to identify the underlying drift function b. Now, there are already methods to estimate this drift coefficient b, but now the question we want to address is how well can one do in this estimation problem in general, no matter which method you use. And so you need to have some notion of efficiency. And in finite dimensional models, there's quite a satisfactory answer to this question, how well can you do in estimating parameters? So if you have a finite dimensional parameter space, so if our function b would lie in a finite dimensional space, then you have the Cramer-Rao lower bound, which says, okay, if the Fisher information is defined by this, which is just the variance of the derivative of the log likelihood with respect to the parameter, and we assume there's one true underlying parameter, theta 0, then there is a bound on all estimators for the true parameter theta 0. So it says the variance of this estimator, that should be a bigger or equal, is bigger than the inverse of this Fisher information matrix. So that both characterizes the optimal convergence rate at which any estimator can converge to the true value, and also the optimal asymptotic variance, so kind of the constant, right? So the convergence rate in the parametric case would be 1 over root n. And now also what we have is, if we look at a Bayesian approach to estimate this parameter, under mild assumptions on the prior distribution, the Bayesian procedure will also attain this best convergence rate, and even with the optimal constant. So that's what we, that's when we say an estimation procedure is asymptotically efficient. Now in infinite dimensions, a similar notion of efficiency is more involved. And also, for example, the rate of convergence at which we can converge to the true parameter is often slower than 1 over root n. So here we see it's slightly worse. And but it's been identified, this what's called minimax rate. And there's also a method which attains the minimax rate. And Richard Nickel and Jakob Züll have proven also that the Bayesian method in the setting of estimation the drift of a diffusion converges to the true parameter in a certain sense at the frequentist minimax rate. But about the constant, we don't know much yet, because this is more involved. So the constant that would be corresponding to the Fisher information thing here And that's what we're trying to address. And we're trying to show that the Bayesian approach is asymptotically efficient. Thanks. Come to my poster.